Hello everyone, and welcome to Lesson 3 of the Structural Geology playlist. Today we are going to be talking about outcrop patterns and structure contours. So let's get right into it. The first thing that we discuss in this chapter is that of a contour map. Hopefully you all are fairly familiar with this sort of idea. Basically, what we have here is an elevation map. And so this ring represents an equal elevation of 10 units, whether that's feet, meters, depends on the map. This ring would represent an equal elevation of 20 meters, and then 30 meters, 40 meters, etc. And so basically this is a top-down view of a map, and it shows equal elevations. So basically this would be the bottom of a valley, because we see that the elevation here is 10 meters, then 20, then 30, then 40. We also have these over here, which represent 20-meter intervals as well. The next thing that's important to recognize whenever we're looking at contour maps is to figure out how structures exist within them. Imagine for a second that we had a horizontal plane that existed in this contour map. Imagine that it's 10 meters thick, and the bottom of the plane is at 20 meters, and the top of the plane is at 30 meters. What this basically means is that this entire section right here, minus these little 20 blobs, this entire section would be where we color in the plane to show where it exists on the surface. So if a researcher were to come walking over here and they were to look at this particular spot, they would see the plane. However, in reality, what we recognize is that most of the time the plane is tilted. It's not going to be a horizontal plane that exists between our contours. And so we have to use a little bit more complicated of a technique to actually evaluate where this plane exists on a contour map. And this is where we get to the idea of a three-point problem. But in order to explain the premise behind a three-point problem, first let me show you a model that actually represents what I'm talking about. So what I've made here is a three-dimensional model of a plane that travels through a body. What you'll recognize is that this purple here is the plane, and the orange is the body in which it travels through. We can recognize that this purple strip is a plane by looking at it along its strike. So if we come over here and look at this plane parallel to its strike, what we recognize is that there is a relatively straight line that exists right here. And that straight line presents the fact that this is indeed a plane. If this were curved, then it would no longer be a plane. It would be a fold. And so the basic idea here is that if we are able to see the entire plane within the body like we are able to do here, then it's fairly easy to determine its characteristics, i.e. its strike and its dip. However, in reality, it's not always that easy. Let me go ahead and demonstrate. Now imagine that this entire surface is covered in foliage, which a lot of the time whenever we're doing geological fieldwork, it is. And this creates a very big problem because now we can't see the entirety of this plane, and it's not so easy to simply look at it from the side and determine what the strike was. Now what we have to recognize is that there's three spots here that are outcropping on the surface. This one, and this one. And so whenever we look at this is still enough data for us to conclude the angle and the strike of the plane. Notably, if we are to connect these points, then we could still get a plane that exists between them and still get the data from that. And I'll go ahead and show you how this is done on pencil and paper. What we have here is a two-dimensional representation of a contour map with 3 points on it that are also on our plane. The basic goal of this exercise is to find 2 points that have the same elevation that are on our plane. The idea behind that is if we can find 2 points that are at the same elevation that are on our plane, we have found our strike. Think, for example, if we were to find, another point right here that was also on our plane. Then of course we would immediately know the strike because we could just draw a line from here to here and that would represent our strike. So the way that we go about figuring out something like this is we draw a line between our highest point and our lowest point, and we find where the elevation of 30 would be along that line. Let me go ahead and demonstrate that. The idea that we're going to try and recognize is to find some point along this line that has an elevation of 30. The reason we're looking for 30 is because this point over here has an elevation of 30, and we need to find 2 points on this plane which have the same elevation. So the way that we figure out what point along this line has an elevation of 30 is we simply measure this line, and in this case we recognize that it's about 13.5 centimeters. And in that case, what we're going to do is we're going to draw a point that is 2/6 along the line from here to here, and then plot that point, and then that will be our 30 point. 2/6 times 13.5 is 4.5, and so we are going to measure 4.5 centimeters from our low point to our high point, and that occurs right here. And so now what we have recognized is that there are 2 points here with the same elevation, and we can draw a line between the two to represent their strike. So at this point you may be questioning, why did I choose 2/6? Well, what we're really going to recognize is that we have a difference right here from our highest point to our lowest point of 60 feet or meters or whatever unit we're using. It goes from 70 to 10. And so 30 is 2/6 between 10 and 70. And the way that you can figure out that fraction is by using this formula down here. Specifically, it's our medium minus our lowest point divided by our highest elevation minus our lowest elevation. And this formula for us gives us 30 minus 10 divided by 70 minus 10, which in this case is 20 over 60, which equals 2/6, or we could call this 1/3. And so this distance right here is 1/3 the distance from here to here. After we have determined our strike, the next thing that we need to do is determine our dip. So what we can do is we can recognize that our dip direction must be perpendicular to our strike. And the way that we look at this is that since this point right here is on the plane, then we must have a perpendicular dip from our strike to this point. And so what I'm going to do is I am going to set up this block, which has a perpendicular corner right here, and I am going to align it so that way this edge is along the strike and this edge represents our dip. And so now we can conclude that this line right here must be our dip direction. And what we will notice is that this is indeed a right angle from our strike. After determining our dip direction, the next step is to figure out our actual dip angle. And the way that we do that is we're going to figure out the horizontal map distance that this line actually covers. And in order to do that, what we're going to need to recognize is what our scale is. And so the scale that I've constructed for this map is that 1 centimeter is equal to 5 feet. The distance along this line is about 4 centimeters. And so since it's 4 centimeters, 4 times 5 is 20. So this distance right here is 20 feet. And so what we can now do is we can use some trigonometry to figure out the dip angle. Let's go ahead and take a look at that triangle here. This has an elevation of 30. This has an elevation of 10. And thus this distance between the two must be 20. So this is 20 feet. And then this also, this horizontal distance, is 20 feet as well. And since this happens to be the same, what we are going to recognize is that this must be a 45-degree angle. But we can go ahead and use some trigonometry to figure that out as well. We know that the tangent of delta is equivalent to 20 over 20. And this implies that the inverse tangent of 1 is delta. Thus, delta must be 45 degrees. And so this has to be our dip angle. So now that we have determined all the different characteristics of our plane, the next exciting step is to figure out where our plane actually intersects with the surface. And the way that we go about doing this is we have to use a piece of tracing paper to write down where our plane is and show where that intersects with our contour map. So what I'm going to do is I'm going to lay my tracing paper over this, and I'm going to represent the plane on my tracing paper. Basically, I'm going to be drawing lines that represent the strike at different heights along the plane. So let me show you what that looks like. So the first line that I have drawn is this 30 line, and this is the strike that we came up with earlier. Basically what I'm concluding here is that this is the strike of the plane, and this plane should have infinitely many strikes that exist at different heights. And so that's what I'm going to do. I'm going to draw lines that are parallel to this at 40 feet, 50 feet, 60 feet, 70 feet, 20 feet, and 10 feet. And the way that I figure out how far these lines should be spaced is by using this equation. That the spacing distance is equal to the contour interval over the tangent of delta. And for us, what this looks like, we know that the contour interval has to be equal to 10 feet, since each one of these contours is separated by 10 feet, divided by tangent of delta. And in this case, that is the tangent of 45 degrees. So we have 10 over 1, which is equal to 10. And so our spacing distance should be 10 feet. But the scale that we came up with earlier, which was that 1 centimeter equals 5 feet, means that each one of these lines going across the paper should be separated by 2 centimeters. So let me go ahead and show you what that looks like. So what I've created here is a representation of our plane and how it exists in plan view. What I want to do now is I want to figure out where it intersects with my actual contour map. And in order to do this, a good solution would be to use a light table. So if you have a table that illuminates light from underneath, this would be a great time to use that. Unfortunately, I do not, so I'm just going to hold this up to my own light and then draw on it with Sharpie. Notice that I have drawn all of the places where the contour map has intersected with my plane. And these are denoted by these blue dots which scatter across my map. As you can see, the way that we would connect these is simply by going over here, coming back up, going around, and going over this way. And what this is going to tell us is the top or the bottom layer of our bedding plane. Let's assume for a moment that this is the bottom layer of our plane, and we're going to go ahead and connect these dots. Also, note that these were drawn on my actual contour map, not on the tracing paper. We're going to need that for later. And so now let's imagine for a second that we found a point that existed at the top of our bedding plane. And let's say that it was this point right here. What we can now do is we can now put our tracing paper on top of this point, matching up the 60, this 60 strike line with this point, and doing the same exercise, noting where it intersects. So note that my tracing paper is not in the same location as it was before. There's a gap here. And so I'm going to get a different set of points that denotes the top layer of this bedding plane. Let me go ahead and show you. After drawing all of the new points on my diagram, here's what I've come up with. Now what you'll notice is if I connect these dots, it's really going to start to look like it actually exists on the surface. And so everything between these two lines is what our plane would look like if it's traveling through this body and exerts itself on the surface. So most of the time we would just color this in and show that this is how our structure would look on the surface. Alright, thank you everyone. That's all I have for today. As always, if you have any questions, just leave them down in the comments and I'll try and get back to you as soon as I can. If you like this video, please like and subscribe. It would be greatly appreciated. Thank you very much.